Take a look at the closest window around you. At this very moment, that sheet of glass is already participating in two separate energy processes, yet neither one is being utilized. During daylight hours, the surface captures portions of sunlight that remain invisible to the human eye. After sunset, it releases heat outward toward the night sky, a region so cold that its temperature rests only a few degrees above absolute zero. These are both continuous energy transfers. They never stop. And in most buildings, they pass by unused. A conventional house loses between 25% and 30% of its heating and cooling energy through its windows. This happens every hour of every day and throughout every season. Now, picture a transparent panel installed wherever a normal window would be placed. In daylight, it produces electricity from sunlight. After dark, it generates power from the temperature contrast between a warm indoor space and the cold sky overhead. There are no moving components, no compressor, no solid surface obstructing the view, no roof alterations. The cooling process does not require a battery. It remains a pane of glass. The difference is that the physical processes occurring within it are no longer wasted. They're captured and converted into useful energy. What exactly is this type of panel? How can it generate electricity after sunset? And why has no version of it appeared in hardware stores? The explanation behind that final question is not rooted in a technological breakdown. The reason is far more uncomfortable. The idea of using windows as passive energy surfaces is not new. For much of history, it simply went by another name. Builders in Roman and Byzantine societies already recognized that openings facing south could gather heat during winter and reduce the amount of fuel required to warm indoor spaces. This was not a matter of style. In Roman bathhouses, sheets of mica and thin pieces of alabaster functioned as early translucent glazing. These materials allowed sunlight to enter while helping stone structures retain warmth. Glass itself is not a modern creation. What changed was its mass production. Across medieval Europe and throughout the Islamic world, architects positioned rooms, courtyards, and window openings according to the seasonal path of the sun rather than street layouts or visual symmetry. Massive stone walls combined with narrow south-facing openings permitted winter sunlight to enter while limiting summer radiation. The structure itself acted as the climate control system. There was no furnace, no thermostat, no electrical expense. The building performed the work through physics, and the builders understood the reasons. A third historical example is even more remarkable. Engineers in Persia and northern India discovered that surfaces exposed to the open sky lose heat through more than just contact with cool air. They also radiate heat directly toward space, a process that continues even when surrounding air temperatures remain relatively mild. In Iran, shallow pools, domed roofs, and specially designed cisterns took advantage of this phenomenon to create ice during winter nights. In some cases, ice formed even though the air temperature never fell below freezing. For these builders, the sky was more than scenery. It served as a thermal reservoir, and they intentionally directed surfaces toward it. None of these developments occurred by accident. They represented deliberate engineering responses to understood physical principles: solar heat gain, thermal mass, material emissivity, and the ability of the open atmosphere to function as a heat sink. The concept of a window acting as a passive energy machine is not a discovery born in a laboratory during 2024. It is an old infrastructure principle that has been largely forgotten and is now returning through the use of modern materials. Research groups at MIT and Stanford approach this challenge from different directions. Teams developing transparent photovoltaic technologies focused on a single question: how can a solar cell produce electricity without blocking visible light? Meanwhile, researchers studying radiative cooling films pursued another objective: creating a surface capable of cooling itself by releasing heat directly to the sky. The modern breakthrough emerges where these two efforts intersect. The daytime operation works in a straightforward way. Traditional silicon solar panels are opaque because they absorb light across the visible spectrum. Transparent photovoltaic systems take a different approach. They employ organic dyes or quantum dot materials that absorb only near infrared and ultraviolet wavelengths. These portions of sunlight cannot be seen by the human eye. Visible light passes through largely unchanged, preserving transparency while still allowing energy collection. When incoming photons are captured, they energize electrons. That flow of electricity is then collected along the perimeter of the panel through ultra-thin conductive pathways built into the frame. To anyone looking at it, the structure still appears to be an ordinary window, yet the glass is performing tasks invisible to human vision. Some versions introduce an additional innovation. A fluorescent layer inside the panel takes in energy and releases it again at a different wavelength. That redirected light is guided through internal channels toward the edges of the frame, where standard solar cells transform it into electrical power. In effect, the glass becomes a conduit for light. The pane gathers energy. The frame handles generation. That arrangement preserves transparency because the energy is redirected sideways rather than converted directly on the viewing surface. The nighttime process relies on an entirely separate set of physical principles. Any object that is warm emits heat in the form of infrared radiation. This is not a technological invention. It is a fundamental law of thermodynamics. Earth's atmosphere is naturally transparent to infrared wavelengths between 8 and 13 micron. As a result, a surface designed to emit strongly within that range can transfer heat directly toward the 3 Kelvin cold of outer space with very little atmospheric interference. With the proper exterior coating, the outside face of a window can reach temperatures 5 to 10 degrees Celsius, lower than the surrounding air during a clear night, all without consuming energy. The same phenomenon explains why frost can appear on vehicle roofs. While air temperatures remain above freezing, the sky is cold, materials correctly oriented toward it become colder as well. Position a thin thermoelectric component between that cooled exterior layer and the warmer surface facing indoors. The result is a generator. No refrigerant is required. No pump operates. No mechanical parts move. A material simply detects a temperature difference and produces voltage. At night, the exterior side remains cold while the interior side retains heat from the room. The panel continuously transforms that temperature contrast into electrical current. The most significant achievement is that both operating modes exist within the same surface and occupy the same installation space. During periods of strong sunlight, transparent energy harvesting is active. When clear nighttime conditions arrive, thermoelectric generation takes over. The panel also prevents part of the sun's heat from entering the building during summer months, reducing the burden placed on cooling systems. The advantages do not arrive one at a time. They accumulate. Early laboratory work at MIT involving transparent luminescent solar concentrators demonstrated power conversion efficiencies ranging from 1% to 5% for completely transparent designs. Lightly tinted versions approach 10%. Taken individually, those figures appear modest. Applied across the full window area of a structure, they become much more significant. For a residence containing 20 square meter of south-facing and west-facing glass, current performance levels could offset between 10% and 20% of the base electrical demand before accounting for any reduction in cooling requirements. A standard double-pane window installed on a south-facing wall contributes a net energy value of 0 over the course of a year. It loses heat during winter. It allows excessive heat during summer. This newer panel changes that same surface into a net positive contributor. There is also a practical experience that numerical data cannot fully describe. No noisy compressor becomes part of the window system. No opaque layer blocks daylight or scenery. During summer, indoor spaces simply feel somewhat cooler. The panel captures energy that would otherwise enter as radiant heat. After sunset, the exterior glass steadily releases heat toward the sky, while the interior environment maintains its temperature for a longer period without relying on active heating. The building depends less on machines operating continuously. Instead, it relies more heavily on material properties and physical laws. That creates a relationship with a building very different from what most people experience in sealed, mechanically ventilated homes, dependent on compressors. So why has this technology not become standard? The answer begins with a genuine limitation. Current fully transparent solar systems remain far less efficient than conventional opaque silicon panels. A rooftop silicon installation converts approximately 20% to 23% of incoming solar energy. A transparent panel converts only 1% to 5%. At present, it cannot compete dollar for dollar with traditional rooftop solar systems. The thermoelectric output produced at night is also measured in milliwatts per square meter rather than watts. Cloud cover reduces both operating modes at the same time. In climates with high humidity, the effectiveness of radiative cooling becomes weaker. Producing quantum dot layers and organic dye coatings is still a complex process. Expanding that production to large scale remains costly and technically challenging. These obstacles are genuine. They carry weight. Yet they do not completely explain why this concept remains near the edge of commercial adoption, instead of becoming a standard feature in new construction projects. Manufacturers of architectural glass earn revenue by supplying certified sealed window assemblies with established thermal performance ratings. Introducing transparent photovoltaic coatings disrupts that category while failing to fit cleanly within existing regulatory frameworks. Current building regulations evaluate windows according to heat transfer performance and solar gain measurements. They do not classify them according to their ability to generate electricity. As a result, no simple certification route exists that allows contractors or developers to satisfy compliance requirements through a straightforward process. Utility companies have limited motivation to speed the adoption of a technology that decreases reliance on the electrical grid one window at a time. Developers constructing multi-unit residential projects generally select window systems that reduce initial expenses. The reason is simple. Residents pay the power bills, developers do not. Because of that, the energy-producing capability of a premium window rarely appears in a developer's financial calculations. Architects and contractors are educated around familiar categories of products. A window capable of producing electricity introduces new installation procedures, different warranty frameworks, and additional insurance considerations. The supply network supporting traditional aluminum-framed glass units is deeply established. It does not easily accommodate a product requiring alternative manufacturing methods, specialized edge treatments, and different verification standards. The technology is unusually passive. It is highly durable. It is distributed across many surfaces. Most importantly, it offers little opportunity for recurring revenue. This is not evidence of a conspiracy. It is a structural challenge. Markets tend to favor products that can be standardized, marketed, serviced, replaced, and rebuilt. A surface that quietly produces power for decades without moving components and without a maintenance contract does not fit comfortably within that model. Even so, the concept can still move forward. Transparent solar films are already available through suppliers focused on sustainable architecture and through specialty glazing manufacturers operating at pilot scale. Glass facing south and west provides the strongest daytime performance. A clear, unobstructed view of the sky on the exterior side provides the strongest nighttime performance. Orientation is not an optional detail, it is the design itself. Not every low emissivity coating performs the same role. Conventional low emissivity glass lowers emissivity to help keep heat indoors. That objective directly opposes the requirement of a radiative cooling exterior layer. Tinted coatings and reflective coatings represent entirely different solutions. Architects working within the passive house movement already optimize glazing placement and solar exposure. Transparent photovoltaic windows represent a direct enhancement of that existing practice. Thermoelectric kits are already available for experimental workshop projects. Research institutions continue releasing open information regarding the fabrication of radiative cooling surfaces. The underlying physics is accessible. Small-scale deployment is already occurring within off-grid communities and among builders focused on sustainable construction. The window has never been a passive object. It never truly was. Roman builders designed stone openings according to the path of the sun. Engineers in Persia directed rooftop structures toward the sky to create ice. Medieval craftsmen embedded seasonal physical principles into wall placement and wall thickness. All of them recognized a common truth. The boundary separating indoors from outdoors was the most influential thermal tool available within a structure. They treated it with that understanding. The principle did not disappear because it failed. It moved aside because conventional glass, sold by the pane, manufactured by the unit, and maintained through established trades, supports an extensive supply chain. A window that creates electricity and gradually pays for itself supports a very different model. Every construction material contains hidden capabilities that modern building categories were never designed to capture. This is only one example. Others remain. If a window can lower temperatures by releasing heat toward the sky above it, imagine what could be achieved with an entire roof engineered around the same concept. Not for one building, for a whole city operating 10 degrees Celsius hotter than the surrounding landscape. That question leads directly into the next stage of the story, where material science may already hold the answer. If you found this discussion valuable, share it with others interested in energy, engineering, and the future of building design. Follow along for the next chapter as the story continues. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.